Okay, let's give you guys some more practice. So establish if this sequence would be monotonically increasing or if it's monotonically decreasing. So press pause and have a go. Okay, so to do this, rewrite this. So rewrite this as two fractions. So here you've got one fraction, and here you've got another fraction. So these two would cancel out, giving you two. So basically, rewrite the sequence as this. Rewrite the sequence as this. Once it's in this form, you can see that it's monotonically decreasing because, well, once you get into this form here, your eye should zoom into this bit here, and then if you look, 1 over x looks like this. So 1 over x squared, which in our case is n squared. It will look like this. It will look like this. But the thing is, n being always positive, we don't really care about the negative side. But you can see that this bubble here, 1 over n squared, is always decreasing. So as n increases towards infinity, this thing here is just going to get smaller and smaller and smaller. So what that means is you start at 2 and then you take away a smaller and smaller and smaller amount as n goes on. So as n moves from 1 all the way to infinity, as n moves from 1 to infinity, this thing here, 1 over n squared, this thing here is just going to get smaller and smaller and smaller and smaller. So you start at 2 and then you take away a smaller and smaller and smaller amount. So that means this thing here must be monotonically increasing. It's always increasing. Once you get to this stage here, you can just glance at this and tell that it's monotonically increasing, because you're taking away a smaller and smaller and smaller amount as time goes on. But if you're not convinced, then turn this sequence into a function and then differentiate it. So you look at the first derivative. The first derivative is always positive because n is always, well, 1 all the way to infinity. It's always positive. It's never in the negative realm. So this is always positive, making the whole thing here always positive. Well, if the gradient is always positive, then it must mean that the function itself, must always be climbing. So therefore, it's always increasing, And then another piece of information that you can obtain is to look at the second derivative. Looking at the second derivative, if you look at this, n is from 1 to infinity. N is always in the positive realm. So this thing here is always positive, and then you've got a negative here. So making the overall thing always negative. Now the second derivative, it being negative all the time, it must mean that the function is concaving down. It wants it to concave down. But then the first derivative is saying that it's always climbing. That it's always the function is always climbing. So this thing here tells us that the function is always climbing. This thing here is telling us that it wants to concave down. So in reality, what's happening is it's always climbing. So you're basically this thing here would tell us that it's bounded from above because it's concaving down. So what the function is really doing is something like this. It's always climbing, but yeah, it wants to concave down. So it's going to do this all the time. It is in effect concaving down because look at this. It is concaving down. Well, anyway, so the second derivative tells us that it's concaving down. It's bounded from above. And if you go back to the sequence here, here you can tell it's bounded by 2 because so basically you would look at this. You would look at it as this. Take the limit of 2 minus blah blah, and then take the limit as n tends to infinity. As n tends to infinity, this is going to be 0. It's bounded by 2 basically. So your sequence will look something like this. It's always climbing, but it's bounded by 2. Okay.